Hello, welcome to the lecture series on engineering thermodynamics. In this session, we will study the second law of thermodynamics. The session outcomes are: we will define heat engine, heat pump, efficiency, and coefficient of performance, in short COP. We state Kelvin, Planck, and Clausius statements of second law of thermodynamics. It is discussed earlier that the first law of thermodynamics is also known as conservation of energy law. So according to this law, all heat can be converted into work and all work can be converted into heat. It is possible heat can flow from high temperature region to low temperature region, and it can also flow from low temperature region to high temperature region. So thus, as far as first law is concerned, all processes are possible. Only thing is, condition is that it should follow conservation of energy. That is, energy is neither created nor destroyed. But it is the second law of thermodynamics which tells whether a given process is possible or not. So whether heat can flow from low temperature body to high temperature body on its own or not. And the second law will explain that. So by experience, heat generated due to braking of a vehicle cannot be converted back into work by cooling the brakes. That is, I said in first law, all heat can be converted into work and all work can be converted into heat. But by experience is what you see. And also, as I mentioned earlier, heat cannot flow from a low temperature body to a high temperature body without any external effort. So let us look into those things. Let us first define the term heat engine. So for that, let me explain with the help of a coordinate system. So let me draw pressure versus velocity. Pressure versus velocity. Let me consider a reciprocating engine. So here, this part is the system I'm considering. Now the system is in equilibrium position because there is a weight acting on that. Of course, there is pressure acting up on the piston. These two are balanced, so it's in the equilibrium state. Right. So now what I can do is I bring a high temperature body here, high temperature body, and start supplying heat to this system. This is what I have shown, high temperature body, this one. So from here, I start supplying heat to the system. As the heat is supplied to the system, the pressure of the system will increase, and this force acting on the piston will be greater than the force or the weight acting downwards. So that the piston will start moving from, say, state 1 to state 2. Right, like this it will move. So let us consider that this is initial state 1 and it will move to state 2, this one. So 1 to 2 is a process. During this process, I have supplied heat to the system and its volume has increased. Fine. Now it is lifting the weight. So that means to say work is being done by the system. In the meantime, heat is being supplied to the system. Now, what is that I am going to do? So we have lifted these things. Next, what I am going to do is, look here. I come back to this point. Now here, I'll just bring a cold body here. I make this heat flow like this. So when I make this heat flow like this, let us say. So now the question is, heat is rejected here. And I bring the system back to its initial state, so that the system has executed a cycle like this. This cycle is what we call it as a thermodynamic cycle. And here, this is what we call it as a heat engine. Means, what is a heat engine? It is defined as a device or a machine, you can say, that should operate in a thermodynamic cycle. Look at this. This is a thermodynamic cycle. It should operate in a thermodynamic cycle. Does a certain amount of net positive work. See, during this process, I have got some work done. As a result of heat transfer from a high temperature body, here, from a high temperature body to the system, and again from the system to a low temperature body. Such a device, I call it as a heat engine. Right? So, please remember the definition of heat engine as it's a device that operates in a thermodynamic cycle. This is a very, very important term. And you should do certain amount of net positive work. Means if there is a negative work also, then you take positive work, net work. As a result of, there should be means heat transfer to the system, again heat transfer from the system to the surroundings. Here from the surroundings to the system, and here from the system to the surrounding. That should happen. Then we call that such a machine, such a device as a heat engine. Let us consider another example. See, another example of heat engine. Here, I have taken a steady flow device, steady flow device, steady flow device, another steady flow device. So these are, these are all control volumes. So into this device boiler, let us say water is entering. To this water, I supply the heat. I convert this water into, say, steam. Steam I expand in the turbine, I get the work. Again, the steam that is exhaust steam that is coming out of the turbine, I condense it. I convert completely into water. Here, a mixture of water vapor and steam will be there. Sorry, water vapor and water will be there. Okay, that when you completely condense it, it will become water. Again, I pump here. Here, I have rejected the heat from the system to the surroundings. Here, I have supplied the heat from the surroundings to the system. Here, I have got a positive work. The system has done work on the surroundings. Here, from the surroundings, I have supplied the work. This is positive work. This is negative work. So, some of these you can call it as network. So, again, it satisfies the definition which I stated earlier. Again, you can call it as an heat engine. Okay. So, this is a heat engine. This one I have shown in another, figure to make you understand better. So now there is something like output. Here I am getting output, but something I am giving input. So the ratio of output to input is called as efficiency. In this, there is what you can call it as thermal energy. Thermal part is involved. We can call this efficiency as thermal efficiency. Thermal efficiency of the heat engine. Right. So now I can define eta thermal. What is that I get? That is net work I get. This is the energy sought for. This was my objective. And to get this is what I'm going to give. For this I pay for. energy that cost and energy I sought for. You know from thermodynamics, W net must be equal to Q net. Earlier I have explained sigma W is equal to sigma Q. So what is W net here? I got positive work. To the pump I gave work. Net work is Wt by minus Wp. So what is the net heat again? This part. It is QH minus QL. So now thermal efficiency is what is net? Okay, QH minus QL is nothing but Wt minus Wp. But what is the input I have given? That is QH. Right? This is what I can call it as thermal efficiency. So Wt minus Wp can also be written as QH minus QL. So we can write like this. This is the thermal efficiency of a heat engine. Sometimes we call it as first law efficiency because it is based on first law. Okay, now you have got an engine. Engine is a power producing device. Now let us define heat pump. Now what really happens over here? For that, let us consider some refrigeration circuit. You see here, low pressure, low temperature refrigerant is entering. Now it is compressed. We supply work here. Here, because of the compression process, temperature increases. Pressure of the refrigerant also increases. It's in the vapor form. It is in the vapor form. Right. This vapor enters into the condenser. Maybe I blow air or I will have a water jacket so that the circulating around that so that heat is removed from this refrigerant. So that here I'll get high pressure, high temperature. Here it was vapor, but here it is liquid. I remove the heat here. Again, I throttle this, which I have explained in the previous topic. So because of the throttling, again its pressure will be low, so and its temperature will be low. As it passes through that from the surroundings, it will start taking the heat, refrigerant. Again, it will become partly vapor and partly liquid, and cycle continues like this. Observe here, this compressor, I'll connect it to an electric motor. I'll connect this electric motor to the lines. From here, I'll give the electrical energy that it will convert into mechanical work and drives the compressor. So work is supplied here. Heat is rejected here to the surroundings. Heat is abstracted from the surroundings here. So here it's a low temperature body. Here it is a high temperature body. I am pumping heat from a low temperature body to high temperature body. So just like we pump water from a sump, if I have a water pump, from the sump, I pump the water to an overhead tank by using a pump. So I call this a water pump. Similarly, I am pumping heat here. I call this device as heat pump. But it works in a cycle. So we can define it's a device which operates in a cycle which requires work, and accomplishes the objective of transferring heat from a low temperature body. So you are keeping fruits, vegetables, food, so many things like that region. It's a low temperature, keeps the temperature lower than its surroundings to a high temperature body. Most of the times it is atmosphere. Such a device we call it as heat pump. So you can see through this figure much better, right? So that is a heat pump. This also should work in a cycle. It should operate in a cycle. And you should pump heat from a low temperature body to a high temperature body. But in this case, we have to supply work. Such a device, we call it as heat pump. So for heat pump, just like we define efficiency for a heat engine, for a heat pump, we define COP, coefficient of performance. Because here again, what is your objective? Either heat should be abstracted and pumped from a low temperature body to high temperature body, or to a cold body we have to pump the heat. So energy sought for, this is the thing, but I am paying for the work here, W. In the previous case engine I was paying for the fuel. Here I am paying for the work. So this way it becomes COP, it becomes Q by W. So there are two cases. Your objective is QH by W, then you can call this device as heat pump. Your objective is, this is QL and that is W. We are keeping the body cooler than the atmosphere, then I can call it as refrigerator. Your objective is to keep the body higher than the body temperature, higher than the surroundings, then I can call this as heat pump. Right? You know that W is nothing but, so already I told you sigma W is equal to sigma Q. So here W can be written as, that is sigma Q is nothing but QH minus QL, and this is QH. That is our objective. Here QL divided by QH minus QL. This is how we can define COP, coefficient of performance. HP means heat pump. Your objective is to keep the temperature of a system higher than that of its surroundings. Here the objective is to keep the system temperature lower than that of its surroundings. That's what COP is. Thermal reservoirs. Thermal reservoir. What is a reservoir? Suppose you have an ocean. Ocean. This is the ocean. If I am to start, I'll connect a water pump here. I start pumping water from here to here. Is its level going to change? No. It is so huge. That's why it's not going to change. This is whatever you pump, this quantity is negligible compared to this. So you may not observe any variation in levels. Then we call this as a reservoir. Similarly, if I start pumping heat from here, let us say initially it has a temperature TH, I start pumping heat from this system. And if temperature is not going to change at all, then it is a thermal reservoir. If it is a high temperature, then it is a high temperature reservoir. We can simulate this. Suppose it's a furnace. You go on taking out heat, but continuously keep burning the fuel and keep the temperature constant. So then you can simulate as a reservoir. Similarly, you go on pumping heat to the atmosphere. This atmosphere temperature may not change at all. Then it is a reservoir. This is at a low temperature. You can call it as a cold reservoir, low temperature reservoir. Okay, there is definitely, don't bring in, sir, global warming is happening and all. That's not the idea over here. Idea is it is so huge, by pumping some heat or ejecting heat from an engine, its temperature increase is infinitesimally small. So that is what we mean by thermal reservoirs. There is a high temperature reservoir and there is a low temperature reservoir. So a thermal reservoir is defined as a body of infinite capacity which is capable of absorbing or rejecting an unlimited quantity of heat without suffering any change in its temperature. The thermal reservoir from which heat QH is transferred to the surrounding operating in a heat engine cycle is called a source. So you can call it as TH, source. I represent like this. This is unlimited. So I take out the heat QH. This is a source. There is a heat engine. It's working in a cycle, let us say, right? It rejection heat QL, let us say, to another reservoir, let us say. And this reservoir temperature is TL, let us say. This is a high temperature reservoir. This is a low temperature reservoir. This is a source. This is a sink. This is a source and this is a sink. Right? The thermal reservoir to which heat QL is transferred from the system during a cycle is called sink. A typical source is a constant temperature furnace where fuel is continuously burnt, and a typical sink is a river or sea or the atmosphere itself. You know, that's why the thermal power plants, they're continuously have to reject a heat or built near a sea or a river where huge water resources are available. Okay, you hope you understood the concept of thermal reservoirs. Let us state second law of thermodynamics. There are two statements, Kelvin-Planck statement and Clausius statement. What is Kelvin-Planck statement says? It is impossible to construct a device which will operate in a cycle. Device operating in a cycle. That means it's an heat engine. Producing no effect other than raising of a weight. That means it should produce work continuously. And exchanging of heat with a single reservoir. I have a reservoir. Let us say its temperature is TH. And it takes the heat QH. And produces the work W, let us say. Such an engine is impossible. That means what it says, it is not possible to convert all heat into work. Okay, this is the heat engine. That is what it means. You cannot have an engine of 100% efficiency. Okay, that is a Kelvin-Planck statement. Now, other one is the Clausius statement. Clausius statement. It is impossible to construct a device which operates in a cycle. Device operates in a cycle. Produces no effect other than transfer of heat. So you have a colder body and you have a hotter body. Let us say its temperature is TL. This temperature is TH. This is taking an heat QL and it is completely transferring the same heat QL. That means it is impossible, like heat itself cannot flow from a low temperature body to high temperature body. It is impossible. That's what the Clausius statement is. So which statement to follow? Now we can, in the subsequent sections, we can prove that Kelvin-Planck statement and Clausius statement are one and the same. Equivalence of Kelvin-Planck and Clausius statement. If I say if I violate Clausius statement, it's same as it is equivalent to violating Kelvin-Planck statement. Now let me consider an engine. There is a source, there is a sink, there is an heat engine. This heat engine is taking a heat QH from the source, rejecting an heat QL and producing a network QH minus QL. Perfect. It is not violating Kelvin-Planck statement. Now let us consider a heat pump. It is taking an heat QH, rejecting an heat QH. Correct? Heat itself is flowing from low temperature body to high temperature body. It is violation of class statement. What you require here is QH. What this assume that this is possible. What it is rejecting is QH, and what it requires is QH. Let me connect these two by a superconductor like this. Now this whole thing you can consider as an engine now. Correct? So this is producing a net work QH minus QL and exchanging heat with a single reservoir. That means it is violating Kelvin-Planck statement. So if you violate class A statement, it is same as violating Kelvin-Planck statement. The other way. Let me consider another case. Let us say this heat engine is taking a heat QH from the source at TH, and it is not rejecting any heat to a low temperature reservoir, converting all heat into work. So that's why W is equal to QH. I will give you W to this heat pump so that it will take the heat QL from the low temperature. Then it will supply this plus this amount of heat to the source. It was taking QH. Out of this QH plus QL given, I will give back to this QH. That means QL on its own is flowing from low temperature body to high temperature body, which is violation of class A statement. So if you violate Kelvin-Planck statement, it is same as violating class A statement. If you violate class A statement, it is same as violating Kelvin-Planck statement. Thus, both class A and Kelvin-Planck statement are equivalent. So earlier we discussed perpetual motion machine of first kind. That means without giving any input, it is impossible to get the output. What is this perpetual motion machine of the second kind? Now look here. I have an engine, heat engine. It is taking heat QH from a thermal reservoir, let us say which is at temperature TH, and it is producing work W, which is equal to QH. It is not exchanging heat with a single reservoir. What it means? All heat is being converted into work. That means the efficiency of this engine is 100%. If such an engine is possible, means then you are violating Kelvin-Planck statement. Such an engine is impossible. That is what we say perpetual motion machine of second kind. It is impossible to build an engine which will have 100% thermal efficiency. Without violating the first law, a machine can be imagined which would continuously absorb heat from a single thermal reservoir, would convert this heat completely into work. So you see here in the perpetual motion machine of the first kind, we are not giving any input. So now here we are giving input, so we are not violating the first law. But though we give this input, all this input cannot be converted into work. That means engine of 100% efficiency is not possible. Perpetual motion machine of second kind is not possible. So we'll continue the discussion in the next session. So you can watch a YouTube video before moving to the next lecture. Till then, thank you.